Look at what happens right before a steel support beam snaps under extreme pressure. We can see where the stress concentrates and how it deforms. This process is finite element analysis, or FEA. Over the next 6 minutes, our goal is to build this exact simulation from scratch using ADINA software. Aerospace and automotive engineers rely on ADINA to predict exactly how structural components will react to physical forces long before a physical prototype is built. Before we start building, download the ADINA trial, check your license is activated, and confirm administrative privileges. With the software active and your preferences set, you have the functional environment ready to start constructing the simulation. Launch ADINA. The top menu bar and toolbars manage files and drawing tools. Navigate to the Setup menu to configure mathematical units. In the central graphics window, use geometry tools to draw a 3D rectangular beam. To enable the soft or to calculate physical deformation, define the material properties by entering specific constants like Young's modulus and Poisson's ratio. After entering those values, check the hierarchical model tree on the side of your screen. You will see your newly defined material populate the list. Assigning these mathematical properties provides the solver with the data it needs to treat the geometry as a specific physical material. Next is meshing. The software divides your solid structure into thousands of smaller, manageable mathematical pieces called finite elements. Creating this grid structure isolates the complex differential equations, allowing ADINA to accurately calculate the behavior of the entire model piece by piece. Apply a fixed boundary condition to one end of your meshed beam. Without this anchor, your solver will fail, causing the object to continuously accelerate through empty space. Once secured, apply an external downward physical force to the opposite end. Without these rigid boundary constraints and directional loads, your mesh remains an abstract calculation with no physical context or purpose. We have our geometry, our material, and our forces. From the menu, select the Static Analysis type and initiate the mathematical solver. Monitor the output window at the bottom of your screen. This verifies that the equations are processing correctly and will eventually display a success message. Once the calculation finishes, open the post-processing toolset to translate that raw mathematical success into a visual format. You will see your standard uniform mesh dynamically shift. It deforms and paints itself with a color-coded gradient, scaling from cool blue to hot red to represent areas of physical stress. The static analysis solver processes the thousands of isolated geometry equations and outputs a single cohesive prediction of how the structure behaves under load. When reading your final post-processed visual, look directly at those colored areas. The deep red zones highlight exactly where the structure is experiencing the highest internal stress. This 2D line graph plots distance against stress. Generating a deflection curve graph like this allows you to measure the exact quantitative path of the physical bend. Congratulations on completing the model. Now try altering the physical force load or increasing the mesh density to observe how the resulting data changes. Mastering these fundamental FEA steps equips engineers with the capacity to test, push, and safely break complex structures entirely in the virtual world, long before physical manufacturing ever begins.